Okay, so I see where I left off at the end of the video that I was making, and at this point I had created a new component called plate, and I made it a blue color, and we're gonna go to Tools, Organize. I may have done this already. Elements that are displayed, I'm going to copy them into this plate. Let me redo that. Make sure I hit copy. I copy them into the plate. Now, if I turn off the plate, I still have these other elements behind it. And I want to turn off everything else in my model except for the plate, and I want to get rid of those temporary nodes. So I'm going to go to temp nodes and clear. Again, I may have done this on the previous video. Oops. Temp nodes, I hit the wrong button. I want to clear all the temp nodes. And I need to do a couple things. I need to equivalence my mesh, and I need to check for normals. Now, this was the spot that I was getting a little hung up on, and I had paused the video. Let's take a look at the equivalenced mesh. We're going to go into 2D. We're going to Tools, Edges. We're going to select the displayed elements with a 0.1 tolerance, and we're going to preview. We're going to find the edges first, and we can see these red lines. These red lines are the edges. We don't want these red lines in here. That indicates a discontinuity, a disconnection between the elements in this mesh. So we're going to go through and select the displayed elements. We're going to preview the equivalence, and the equivalence nodes look like they're in the right spots. We're going to go ahead and do the 0.1, and we're going to equivalence it. And then we're going to go and find edges again. And now you notice that we don't have any interior edges, so everything's looking good. I'm going to turn off this edge display and just leave the plate up here. And we need to check for normals. In Tools, we're going to go Normals. We're going to go the plate component. We're going to select it and display our normals. Now I'm going to rotate this, and you see all of our normals are happening to point in the same direction. Now sometimes you will see a few elements that if you do these things by hand, you may end up with some elements whose normals are pointing in the opposite direction. Let's change one, and I'll show you what you can do to get things straightened out. I'm just going to reverse this one. I might have reversed them all. Let's see. Oh, there's one. Okay. So I just reversed one of them. And you may have two or three that are reversed. As you travel around your element, you should go in the same sense of rotation, like counterclockwise. And I'll show you in just a second what that means. But if you have a normal that is pointing in the wrong direction or opposite from all the others, what you can do is you can select an orientation element and adjust all the normals, and now you see that one flipped back to the right way. Okay, so that's good. Let's do this. Let's talk about normals and elements real quick. Let me show my sketch pad. So I sketched a couple of elements, and here I have a element nodes 1, 2, 3, and 4. And if I use my right hand and use the right hand rule as if I'm going from 1 to 2 to 3 to 4, the plane that's formed by those 4 nodes has a unit normal, and that unit normal by the right hand rule will point upward out of that element. If my element numbering was reversed, as I have in this second picture, 1, 2, 3, 4 that way, my right hand rule would have a unit normal that points down into the page. Okay? So the element connectivity determines the orientation of the unit normal. So as you make those triangle elements, if you consistently go 1, 2, 3 in a counterclockwise fashion, you will have the right direction for all those unit normals. It's no big deal. However, you do need to get them all straightened out before you export the mesh. So that's where we're at now. We're getting ready to export the mesh. I'm going to go to File, Export, Solver Deck, and I'm going to call this optimized plate.inp. And this is really important. I'm only going to export what is displayed, and I only want to have what is displayed is the thing that I want to export, which is this plate component. Okay, I'm going to hit export. I had done this previously, so it's going to ask if I'm going to override it. I'm going to say yes. Now let's look at that file. Okay. If we look at that file, at the beginning of it, I'm using Crimson Editor. And just as a little side note, Crimson Editor is a great freeware text editor. I'd highly recommend it for these kind of files. Input files can be pretty big. You do not want to use Notepad or WordPad. You want to use something a little more sophisticated than the basic Windows tools. So Notepad++ would work, or some of these other text editors that can read really big files will work. I really like Crimson Editor, and just by coincidence it was developed at the University of Alabama a number of years ago. Right, now if we look in here, here's the section where it says nodes. This is the node number, this is the coordinates of that node, X, Y, and Z. If we scroll down here, we get to the elements. Okay, these are the 3 noded elements, and these are the 4 noded elements. What we want to do is we want to use the same elements as what we had in our previous analysis. Now, in order to figure out what we had in our previous analysis, we need to go to our temporary directory, wherever it is that we're doing our calculations at. I think it's here. And we want to open up one of these files, and we want to see what elements that ABAQUS had us use when we weren't really paying attention to anything. So let's scroll down here and take a look at the elements. We're going to write this down, CPS3 and CPS4R. Now before we import this mesh into ABAQUS, we want to go in here, we want to change this to CPS3 and CPS4R and save this file. Now it doesn't matter that we don't have any materials in here or anything else like that. We're not going to run this directly. If you wanted to, you could use HyperMesh and you can do all of that. I've found that it's pretty easy to specify loads and boundary conditions in ABAQUS. So I tend to use HyperMesh just for generating the mesh. Alright, let's get into, let's go over to ABAQUS. And I am going to go to Model. And I had done this, so I'm going to delete this so we can go through all the steps. But I'm going to go File, Import a Model, and I'm going to select the INP, Optimized Plate.inp. I'm going to bring that in. Now right now we don't have any material properties, all we have is the mesh. Anything else? Now notice your previous model is still in here. You can have multiple models inside of the model database. The CAE file can contain multiple kind of independent models. Okay, let's start from the top. We're going to go to Properties. We were using steel, so let's go Mechanical Elasticity. If I can scoot that over right. We're in the millimeter system, so 210,000. Oops. Need to turn on my number lock. And 0.3 for Poisson's ratio. All the rest is defaults are fine. We've done this a few times now. We're going to create a section, solid homogeneous, it's fine, and a plane stress thickness of 1 millimeter, just like we had before. Now we're going to assign the section. We're going to select this entire plate and hit Done and assign it section 1, and there we are. Alright, next thing we want to do, we don't need an assembly. We're going to go to the step. We are going to create a step. Step 1 is going to be a static general analysis. All the defaults are fine. I'm going a little quicker than I had been before. But we're going to go into initial and we're going to set boundary conditions, and we're going to go then into step 1 and put in the load. So the initial step, I'm going to right click on the boundary conditions. I'm going to create a boundary condition, which is going to be displacement type, and I'm going to select all the nodes on the bottom of this mesh. See how all these just lit up after I did that? And I'm going to say that they cannot have any displacement in the, let's think about this, we don't want them to have any displacement in the vertical direction, just like we did before. Okay. Now we're going to create another one, same type, displacement, and we're going to select all the nodes on the left edge. Okay. And on that one, we don't want any displacement in the x direction because of the symmetry boundary conditions like we talked about. Let's make this a little bit smaller. We're going to go into step 1 and we're going to create a load. It's going to be a pressure load, and we're going to select this top surface. And notice it's kind of over selected. It has some edges over here. We don't want pressure on those things. So what I'm going to do to deselect them is I'm going to go and on my keyboard I'm pressing the control button, and I'm going to left click on my mouse and see how that disappeared. So control, hover over it till it kind of goes orange, click on it, and then it disappears. So that's the way to deselect something. Okay, that's what we want, and it's going to be uniform pressure. And if we remember what we did last time, we used minus 0.8 megapascals because we want that to correspond to a nominal stress of 1. And we hit OK. All the defaults are fine. So we're going to create a job. Let's call this optimized. The model will be optimized plate. Make sure that's selected. All the defaults are fine. And we're going to go here and we're going to right click and hit submit. Now hopefully there won't be any errors, but if there are, we'll take care of them. It's going through its pre-processing phase. Here it's reading the input file, making sure everything makes sense. Okay, the input file is completed successfully and the job completed successfully. So let's take a look at our results. I'm going to right click and load in the results. And I'm going to select the S22 stress. And here it is. Seems to be a little bit high, and there's it's not what I got just a minute ago. I think there's some error. I think we have an extra node selected for a boundary condition. Let's go back here. See how that blue is down there. That shouldn't be that way. Let's go back to our model and just check it out. Let's zoom in on this a little bit. And you know what? I selected a couple of extra nodes for the boundary conditions. So let's fix that. Okay. What I'm going to do, since it's in boundary condition 1, I'm going to edit them. Okay, and I am going to hit my control button on the keyboard. Let's see if I can get rid of those. Okay, I need to hit this edit region. Now the control on the keyboard. Let's see if that works. Alright, I tell you what we're going to do. We ought to be able to edit those, but I'm just going to hit... let me pause it and let me figure out exactly what I need to do. Okay, so what I'm going to do then is we're going to go here to Tools, Set, Edit, Set to, and let's zoom in a little bit so we have a little easier time. Okay, and Now it says reselect the nodes for the set individually, or we can do it by angle. Let's try one more time to do it individually. And I'm going to make a box. And what I did is I just selected a little too high up. Okay, and I'm going to reselect and hit done. Okay, and those nodes are selected. Okay, so this may happen to you as well. So just zoom in there and make sure that your nodes are properly selected for that bottom edge. And while we're here, let's just zoom in on this side, make sure I didn't get too far. That side looks good. Alright, let's try this again then. Optimize, let's resubmit it. Overwrite those files. And it should just take a few moments to go through here and do that. Alright, it's completed, so we're going to right click and look at the results. I don't know what that error is, but we're going to go through and look at the S22 stress. And okay, this is what I had gotten previously, 2.527. Now you see the contour is a little more coarse around here, but if we're not so interested in those stresses, but we're interested in the value of the stress concentration factor, we have 2.527 for our stress concentration factor, and let's see how many elements we've got. We got tools, we're going to go tools, query, mesh. We only have 252 elements. Let's go back to our Excel file. We have 252 elements with a stress concentration factor of 2.527. Let's add some numbers to this. See if I can do that. Okay, so these are so few elements, it almost looks like it's close to zero. But we have pretty much the converged value. It's in between 2.516 and 2.612. So I would consider that a good converged value for the stress concentration factor. Now, if you're really good and experienced with building finite element meshes, you could start off with an optimized mesh that looks pretty much like this and get pretty close to what we would expect to be the right answer for our particular stress analysis. Now, I will say, particularly for academic use, I am very picky when I'm on a student's committee and they do finite element analysis and they haven't done a convergence analysis. We really need to know how good is our answer. And from this point on in the course, whenever we do a finite element mesh, we need to keep that in mind, that we should do a convergence analysis to see if our answers change with the mesh. If the answers stop changing with the mesh, then we have a converged result. In industry, sometimes they take a little bit different approach. In the automotive industry, for example, if they're looking at sheet metal, they may have a standard size element for sheet metal, and they may use 5mm elements. And that's maybe coarse in some areas, but they have enough experience knowing that if they get a stress result, they should maybe multiply it by 10% to get the answer for the stresses near that spot. Some things can be pretty complicated to model, and they may not just be interested in stresses, they might be interested in displacements, natural frequencies, or something like that that maybe doesn't require as fine of a mesh. In our class and for your academic career, I'd really urge you to do convergence analyses for any finite element analysis that you do. And it's something that you do need to keep in mind if you're a practicing engineer, that you're going to need to understand convergence behavior. Alright, so I think this was good. We got a chance to construct this mesh and hypermesh, import it into ABAQUS, and come up with our optimized mesh.